Hi there, this is Mr. Schnitzius, and in this video we are looking at an embedded assessment 3 right at the end of Unit 5. This is from page 549 if you're following along in the PDF in the Unit 5 ebook, and this is titled Changing Dimensions of Spheres, Spherical Storage. Storage vessels containing organic liquids should be designed and built according to the American Petroleum Institute API 650 specification. Storage vessels come in various shapes and sizes, but in general, most are installed within a containment basin for safety reasons. Some vessels need to be pressurized if they are being used to store organic liquids with high vapor pressures. Typically, the best design for this application, however costly, is a sphere. A petroleum company plans to purchase some spherical pressurized storage vessels. The process engineering group and the purchasing department are working together to analyze possible options. All right, so just like we do on all these embedded assessments, I'm strongly encouraging you that you pause the video, answer all 5 questions, and then unpause it, and we'll go over the answers together. Okay, so in number 1, they want us to fill in some measurements, either the diameter or the surface area or the volume, depending on what's given to us. So we'll start off with a pretty easy one. For vessel A, they tell us that the diameter is 20 meters. So if the whole diameter is 20 meters, that means that the radius is going to be half of that, which is 10 meters. So they want us to both work out the surface area, and we know from our Unit 5 learning that the surface area formula for a sphere is 4 times pi times the radius squared. So we're going to substitute, and that's going to be 4 times pi times 10 meters squared. So part of this we're going to work out exactly. I can actually put an equal sign. 10 squared is 100. 4 times 100 is 400 pi meters squared. But in order to compute costs, like if we need to know how many square meters of material to use at Home Depot, or when we're dealing with a supplier that we are ordering from, they might be a little confused if we order in terms of pi. So we might want to know what that is as a decimal. If you put 400 times pi into your calculator, that will come out to be 1,256.64 to the nearest hundredth meter squared. So we're going to do the same thing with the volume now. The volume formula for a sphere is 4/3 times pi r cubed. So we're simply going to substitute 10 meters for the radius. Okay, so we'll break this one down a little bit. That's 4/3 times pi. 10 meters to the third would be 1,000 meters cubed. All right, and since 1,000 is not divisible by 3, we're going to leave this as 4,000 pi over 3 cubic meters. And if we round that to a decimal, that's going to be 4,188.79 meters cubed. So there are the first 2 measurements. For vessel B, they're going to ask us to work backwards, okay? They're going to tell us the volume, and then we are going to need to find the diameter and the surface area. Well, since the surface area depends on the radius, which we can use to help us get the diameter, we're going to solve for what the diameter is first, and then after we know that, we'll be able to solve for the surface area. So let's use that same volume formula that we used right here. 4 pi r cubed is the volume for a sphere, and we're supposed to set that equal to 33,510.3 meters cubed. That's equal to 4/3 pi r to the third. Well, if our goal is to find out what the radius, a good first step would be to divide both sides by 4/3 pi. Remember, pi is a number, so it's okay to divide like that. So those cancel out. And our calculator is going to tell us about what this is equal to. So we want that to be 33,510.3. Now it's very, very important that we use parentheses here. So we want to divide by the fraction 4/3. We want to multiply that times pi. So now 7,999.99. That is really, really close to 8,000. So we're actually going to round that right on up to 8,000. And now when we take the cube root of both sides, the cube root of 8,000 comes out to be 20 meters. If you don't believe me, just think about what 2 to the third power is. That's 8. And then multiplying 3 20s together, there would be 3 zeros. So bam, that's why those are there. So if the radius is 20 meters, that means that the whole diameter would be 40 meters. And then now that we know that the radius is 20 meters, we can pretty easily use that to get the surface area. That's going to be 4 times pi times the radius squared. So that's going to be 4 times pi times 20 meters squared. Well, let's see, 20 squared is 400. 400 times 4 is 1,600. This is going to be 1,600 pi meters squared. Or as a decimal, we can write that out as 5,026 to the nearest hundredth, 0.55 meters squared. Okie dokie. So there are our diameter and surface area for vessel B. Vessel C is going to be a little bit easier, I think, since the surface area formula is a little bit easier to deal with than the volume formula. Just like we did with vessel B, we're going to solve for the radius first, then that'll tell us the diameter. Then once we know the radius, we'll be able to find the volume as well. All right, so since the surface area formula for a sphere is 4 times pi times r squared, we're going to set the given surface area for vessel C equal to that. Equals 4 times pi times r squared. This will also be a little bit easier to solve out because dividing by 4 pi in the calculator is going to be a little more simple than dividing by 4/3 pi. So those cancel out. And what do we have left over after we do that? Well, let's use our handy dandy calculator to help us figure that out. 11,309.7. Again, we're going to divide by using parentheses, divided by 4 pi. And just like we ended up with a decimal that rounded up, 899.997, that's really extraordinarily close to 900. So we're going to go ahead and round that r squared up to 900 meters squared. We want to know what r is, so we want to cancel out the exponent of 2. So that's going to give us that r is 30 meters. So if the radius is 30 meters, then double that would be a diameter of 60 meters. And if we know that the radius is 30 meters, we can plug that into the volume formula of 4/3 times pi times the radius to the third power. Let's see, 4/3 times pi, 30 to the 30th. Well, 30 to the third can be done pretty easily in your head. What's 3 to the third? 3 times 3 is 9, times another 3 is 27. Then we've got these 3 zeros on the end, so that's going to be 27,000 meters cubed. Okay. This we can still do in our head though. 27 divided by 3 is 9, so this is 9,000. We divide it by 3, but times 4 is 36,000, so this is going to be 36,000 pi meters cubed. But as a decimal, if we were to put 36,000 pi into the calculator, we would get 113,097.0 cubic meters. So that's just practicing those surface area and volume formulas a little bit, re-upping your algebra skills, making sure that you're confident with those. So now number 2 says the company plans to have the tanks painted after they are installed. Describe the effect that doubling the diameter has on the amount of paint needed to paint the tanks, and what happens when the diameter is increased by a factor of 3. Well, the amount of paint needed to paint the tanks, is that a surface area calculation or a volume calculation? And the way you can answer that question is that a question involving the inside of the tank or the outside of the tank? How much the tank can hold or what goes around the outside of the tank? They're painting the outside of the tank, so this would be a surface area calculation. All right, and we learned in our changing dimensions activity in activity 37 that the ratio of the surface areas is equal to the scale factor, but since area is a two-dimensional measurement, since we measure area in squared units, we take the scale factor and we square it. So if we doubled the diameter, that would be the same as doubling the radius. That would give us a scale factor of 2. Squaring that 2 would give us a factor of 4 times as much paint. And if we increase the diameter by a factor of 3, then squaring that scale factor of 3 would give us a surface area ratio of 9 times as much paint. Number 3 says, describe the effect that doubling the diameter has on the capacity of a spherical storage vessel. Well, capacity means how much it can hold. How much it can hold is a volume question. Okay, so whereas the ratio of the surface areas is equal to the scale factor squared, since surface area is measured in square units, the ratio of the volumes between two similar solids also depends on the scale factor, sorry about that, also depends on the scale factor, there we go, but it depends on the scale factor raised to the third power. Why is that? Because volume is a three-dimensional measurement. So doubling the diameter increases the volume by a factor of 2 to the third, which would be 8 times larger. And tripling the diameter increases the volume by a factor of 3 to the third, which would be 27 times larger. All right, just a couple more problems here. How would the amount of paint needed and the capacity change if the company chose a storage vessel with a diameter that was half as large as the diameter of vessel A? Well, if the diameter is half as large, that's telling us that the scale factor used to create that new storage vessel would be 1/2. Multiply the radius times 1/2. So if we did that, we would need only 1/4 of the amount of paint needed for vessel A. And why is that? Because that's a surface area calculation. If we take our scale factor of 1/2 and we square it, we would get a surface area that's 1/4 of the original surface area. The capacity would be 1/8 the capacity of vessel A. And the way that we could show our work for that is, since volume is a cubic measurement, we would take the scale factor, we would cube it, and that would give us the reduction factor for the volume. And then they're going to spend the rest of this explanation kind of putting in words what we just worked out right here. I guess one thing that we would maybe want to note, when you're applying an exponent to a fraction, that exponent gets applied to the numerator and the denominator. That might look a little different here than what they have down here because 1 to any power is just 1. So this and this are the same thing. They left out that step where they applied the exponent to the 1 as well. All right, last problem. The support for the tanks are in the shapes of cylinders. The supports for vessel A and vessel C are similar. Each support for vessel A has volume 450,000 pi centimeters cubed and surface area 60,450 pi centimeters cubed. If the volume of each cylindrical support for vessel C is 1,518,750 pi centimeters cubed, write a proportion that can be used to determine the surface area of each of vessel C's supports. Explain how you arrive at the answer. Okay, so their final proportion is this: 9/4 equals x over 60,450 pi. All right, so let's look at how they got that. So we've got a ratio for the volumes. So this is a ratio of vessel C compared to vessel A. All right, so if you reduce this down, you get 27/8. Well, this is a ratio of the volumes. This is I believe that's the way that we wrote it out right here. Yep. So the ratio of the volumes. Well, we had solved a problem before where we knew the scale factor and we applied that exponent of 3 to the scale factor to get the ratio of the volumes. Let's say that you wanted to figure out the scale factor if you knew the ratio of the volumes, though. Well, to undo this exponent of 3, to move it to the other side of the equation, you would have to undo that exponent of 3. How do you do that? Well, what's the opposite of cubing something? It's taking the cube root. So if you know the ratio of the volumes, and you take the cube root of that ratio, that's going to tell you what the scale factor is. So that's all they did right here. They did the cube root of the ratio of the volumes. So this 3/2 gave them their scale factor. And now we know that if we know the scale factor, we can square that scale factor, and that'll tell us the ratio of the areas and also the ratio of the surface areas. So this right here is the ratio of the surface areas. And since we know the surface area for vessel A, we can drop that underneath, and then if we solve this proportion for x, it'll tell us the surface area for vessel C. So that's it for this embedded assessment. Thank you guys so much for your hard work. Good luck on your Unit 5 quiz, or if you're reviewing for the final exam, study hard. We're very proud of all your work.